All right, welcome to the Explainer. Today, we're putting on our high-tech consultant hats to evaluate what I can only describe as a massive, absolute disruption in the field of quantum thermometry. We're talking about the GlyD QSense. We're going to dive deep into the master implementation plan for this tech, essentially acting as a technical guide for materials researchers, medical experts, and tech investors. We'll be looking at how this project takes seriously complex quantum physics and packages it into a highly accessible, totally biodegradable format that's basically poised to change everything from clinical oncology to industrial quality control. So here's our roadmap for today. We'll breeze through the quantum revolution, the physics of the silent window, synthesis and AI protocols, clinical oncology validation, industry scale, and finally the budget and blockchain implementation. Let's jump right in. Section 1, the quantum revolution. For years, if you wanted high-precision temperature sensing, you were pretty much stuck with nitrogen vacancy centers inside synthetic nanodiamonds. But let's be real, that standard comes with some severe baggage. They literally cost millions of euros in rigid infrastructure. And worse, they're biopersistent, carrying potential long-term toxicity risks. By stark contrast, the new organic GlyD QSense completely democratizes this technology. It requires a radically lower investment of just 72,000 euros. And because it's an organic sensor made of completely deuterated gamma-phase glycine, it is 100% biocompatible and biodegradable. I mean, it's a total paradigm shift. Section 2, Physics and the Silent Window. Okay, so how exactly does a biodegradable crystal pull off quantum-level precision? To explain this complex physics concept to any students or newcomers listening, think of it this way. Imagine you're trying to listen to a specific, very quiet radio station, but you're standing in the middle of a massive, screamingly noisy city. All that background noise makes it impossible to hear the music, right? Well, in biological tissues, carbon-hydrogen bonds act just like that noisy city. They create massive background interference, autofluorescence, that drowns out traditional sensors. The silent window is like tuning your radio to a specialized, crystal-clear frequency that the city noise simply can't reach. By entirely substituting the hydrogen in the crystal with deuterium, the sensor shifts its molecular vibrations to a spectral region between 2100 and 2300 inverse centimeters. That is a zone completely free of biological static. The key takeaway here is that by shifting the frequency to an exact number, specifically 2120 inverse centimeters, using isotopic substitution, the sensor achieves near total optical transparency in living tissues. You get a maximum signal-to-noise ratio, which allows for incredibly precise readings without any of that biological interference getting in the way. Section 3, Synthesis and AI Protocol. For the materials researchers tuning in, here is exactly how these organic crystals are made. The step-by-step protocol for synthesizing these glycine crystals is meticulous, but it's highly accessible. It kicks off with dissolving deuterated glycine in heavy water at 45 degrees Celsius. Next comes a really critical PTFE filtration step to remove any premature crystallization nuclei. Then, microfluidic mixing is performed with cold deuterated ethanol at extremely specific flow rates. We're talking 0.5 and 0.8 microliters per minute. Now, this whole thing is executed under an ultra-pure argon atmosphere to prevent even a hint of moisture contamination. Finally, gamma-phase seeds are added for phase induction, followed by 24 hours of vacuum drying. This optimized process gives you the exact hexagonal prisms that have the piezoelectric and pyroelectric properties required for quantum thermal sensing. But, hardware always needs software. A crystal alone doesn't just magically give you a temperature readout. You actually have to decode the slight shifts in its molecular vibrations. So to do this, the research team generated a massive dataset, 18,300 synthetic spectra, modeling the sensor's thermal response between 15 and 45 degrees Celsius. They used this massive corpus to train a highly specialized, one-dimensional convolutional neural network. And what makes this AI architecture so fundamentally revolutionary is how it completely upgrades the measurement process. Traditionally, analyzing these spectral shifts required some really complex manual curve fitting models. But this 1D CNN, it entirely eliminates clunky curve fitting by directly capturing the anharmonic physics of the crystal. It uses blocks of 128, 256, and 512 filters to extract features, applies asymmetric least squares for baseline correction, and uses a mix-up technique during training. This makes sure the model stays incredibly robust, even if there are variations in the laser power or a bit of instrumental drift. The final result is a clinical-grade mean absolute error of just 0.08 degrees Celsius. Absolutely wild. Section 4, Clinical Oncology Validation. Now we have to look at the irrefutable proof of this tech's safety. The in vitro validation conducted using HeLa cells is a huge win for biocompatibility. After coating the nanocrystals to ensure colloidal stability, they hit a 70% internalization efficiency. But most importantly, cell viability stayed at a massive 92% after 24 hours. This definitively proves the sensor's incredible safety profile. On top of that, the sensor showed a 50% degradation of its Raman signal at 48 hours. This controlled biodegradation means there is zero long-term nanomaterial persistence in the patient's body. That is a massive strategic advantage over those persistent, potentially toxic nanodiamonds we talked about earlier.
So what does this actually mean for medical experts and oncological surgeons operating in high-stakes environments? Well, it translates directly to life-saving capabilities. By leveraging that tiny 0.08 degrees Celsius margin of error, surgeons can map exact tumor margins in real time. Because cancerous tissues often have slightly different metabolic rates and thermal signatures compared to healthy ones, surgeons using GlyD QSense can measure exact tissue thermal changes during procedures. This precisely guides oncological surgeries and can drastically reduce the rates of surgical recurrence.
Section 5. Industry and Agriculture. But hey, the potential here scales way beyond the hospital operating room. From detecting early water stress in precision agriculture, literally before any visible damage even occurs, to profiling heat management in high-density microchips for industrial quality control, the multidisciplinary versatility of this sensor is just staggering. It can even be used in pharmacology for automated predictive toxicology, or what they call termitox screening, and in defense for monitoring critical components and satellites. Being able to drop a cheap, biodegradable, hyper-accurate temperature sensor into basically any environment completely changes the game for industrial quality assurance.
Section 6. Budget and Blockchain.
Let's break down the core of this high-tech consulting pitch, the actual numbers and profitability. By utilizing perfectly accessible equipment and reagents like deuterated glycine, the entire implementation is remarkably lean. We're looking at 12,500 euros for isotopic reagents, 18,000 for high-end characterization time, 11,000 for the GPU AI compute, and so on, bringing the total implementation cost to just 72,000 euros. Let me reiterate that, 72,000 euros total. That is a microscopic fraction of the cost associated with building a conventional NV Center laboratory. It is a completely validated, highly profitable pathway to market. Furthermore, to guarantee the strategic value for tech investors and institutions, the intellectual property has been meticulously locked down. Alongside priority patents and standard academic repositories, the entire dataset, architectural code, and proof of authorship are cryptographically shielded. They use immutable blockchain registries via the Ethereum network. This guarantees complete traceability and an unalterable timestamp of the innovation, ensuring totally robust legal and commercial control of the asset. So, wrapping all of this up, keeping all these incredible cost savings, the sub-degree AI-driven accuracy, and the vast cross-industry capabilities in mind, I want to leave you with a final thought. With clinical-grade quantum precision now achieved organically at a fraction of the traditional cost, how quickly will organic sensors like GlyD QSense redefine the future of your industry? Thanks for joining me on this explainer, and keep exploring.